In this video, we will observe the effects of light refraction across various surfaces and in differing weather conditions. We'll look at some observations over water, land, and from home. These observations demonstrate how upward light refraction, which makes distant objects appear lower than they actually are, is a common occurrence that is seen day after day in various conditions throughout the year. Although temperature is not the only factor with these observations, generally, when the layer of air near the surface is warmest and the air temperature decreases from there with gain in elevation, distant objects will typically appear to sink. What's more is, they seem to sink exponentially with increase in distance from the viewer. This atmospheric effect can make flat or horizontal surfaces, where no physical obstruction is present, appear convex by creating apparent obstruction of distant objects. And curved or sloped surfaces with some physical obstruction appear more sharply curved and the obstruction greater due to this sinking effect. This effect can even be witnessed over ice, and over water in the evening. First, we will explore observations over small bodies of water. These observations are conducted within 1,000 feet from the viewer and with a viewing height of approximately 2 inches above the water surface. The goal is to get a relative viewing height to the distance of objects that equates to an observer looking over an ocean or large lake at a distant boat or building. For instance, viewing objects at a distance of 600 feet away from 2 inches off the ground is equivalent to an observer viewing objects at 6.8 miles away and from 10 feet above the water surface. We'll use the scale of 1 inch equal to 5 feet to scale down our observations and to see how they correlate to observations over large bodies of water at the same relative distance. As we've pointed out before, curvature cannot be the cause of obstruction in any of the following observations. At a distance of 1,000 feet on a sphere of our given radius, there would be only about 3/10 of an inch of curvature drop, and there can be no obstruction due to curvature. From a viewing height of 2 inches, the geometric horizon would be over 2,600 feet away. So, all effects witnessed in this video cannot be caused by the curvature of the Earth. These effects are all apparent and caused by the surrounding air. Here is a calm day on the lake where we sail an RC boat out. Here, the RC boat is around 300 feet or so, and it is approaching the apparent edge of the waterline. As the boat sails beyond 300 feet from the camera, the boat begins to disappear from the bottom up due to the inferior mirage. As it travels beyond 500 feet, most of the hull can no longer be seen. For this next test, we'll take our RC ship out to just under 1,000 feet from the observer. Here is a look at the size of the RC ship in inches. Here is the ship at around 300 feet from the observer and sailing beyond. By 700 feet or so, the hull of the ship is no longer visible. And as the ship travels just beyond 900 feet, only the very top inch or so of the ship's towers are visible. Observing from 2 inches above the surface at a distance of 900 feet is the equivalent of an observer viewing from 10 feet above the surface at a distance of 10.23 miles. In looking at an object 10.23 miles away, from a viewer's height of 10 feet, the globe model predicts that only about 3 feet should be visible for a distant object that's 30 feet tall. What's interesting is that this inferior mirage, which doesn't allow the light from the bottom of the RC ship to arrive to the viewer, is blocking nearly the same relative amount of the ship that should be blocked by curvature on a sphere of our given radius. Only the top inch or so of the RC ship is visible by the end, which would be equal to 5 feet to scale, closely matching what is witnessed over large bodies of water under certain conditions. Although very common, this sinking effect does not always occur. Different days produce different results. On days when the water is cooler than the air above, and the air temperature increases with the gain in elevation, we're typically able to see distant objects in full, up to a certain point. When this temperature inversion occurs, the light from distant objects is normally able to travel to the viewer in full. And when the temperature inversion is steep enough, the surface can even appear concave. Here are 2 different days looking at objects placed 600 feet from the observer and viewing from the same viewing height of approximately 2 inches above the waterline. On this day, when the air temperature increases with gain in elevation, we're able to see the distant objects in full. And on this other day, when the air near the surface and air above it are about the same temperatures, but the water is just a bit warmer, we witness upward refraction as the light from the bottom of the distant objects does not arrive to the viewer. We have to raise our viewing height to receive the light from the objects in full. The air on this day displaces the distant objects, making them appear to sink, and also seems to enlarge them. In reality, the objects are likely higher up, but we're looking down into the water to make this observation due to sinking refraction. This effect creates an apparent edge to the waterline that appears much closer to the viewer than where the waterline actually is at the opposite shore. Here is another look at each day. Although we're sometimes able to see distant objects in full on days with a temperature inversion, other times we're not, as compression can make distant objects still seem to disappear bottom up. As the boat reaches 600 feet from the observer, only the sail is visible. We have to raise our viewing height to see the hull of the boat.